Yes, we will start the session. Good morning to all. We have completed 4 days, 4 topics. On 4 topics, we have covered the faculty development program till today. So today is the last day, and I welcome you all for the today's webinar faculty. So already our today's speaker is already joined. So without delay, we will start the session today. So our faculty development program on advanced materials and manufacturing systems. So the today's topic is friction stir processing. Yeah, today's process friction stir processing. It is a novel surface modifying technique that provides microstructural modification and control in the near surface layer of the metal components. So we can say that actually it refines the microstructure and it improves the properties of the metal. And in detail, sir will be taking on this friction stir processing. So before taking session, I would like to introduce Dr. R. Aroki Kumar sir. So I thank you, sir, for accepting our invitation. So now I will be introducing him, sir. Dr. Aroki Kumar sir is a assistant professor at NIT Warangal in Department of Metallurgical and Material Engineering. Sir did PhD, Sir did BE Mechanical Engineering from Madurai, Tamil Nadu, RCET College, and MTech in Material Science from NIT Tiruchirappalli, and PhD in Material Science and Engineering from KAIST, KAIST, Daejeon. It is in South Korea. Started in PhD in Material Science Engineering from South Korea, and he has been working as assistant professor from NIT in NIT Warangal since 2014 onwards. And also he did his postdoctoral research in South Korea, Japan, and in NIT Tiruchirappalli also. And he's a peer reviewer in well reputed journals like Journal of Alloys and Compounds, which is a high impact factor journal, and Material Science and Engineering A, Material Science and Engineering B. So he's the editor, and he has published more than 11 international journal papers and guided many MTech thesis, and also PhD is guiding PhD thesis also more than. So much of research work he has done, and he was awarded as a INAE teacher membership program. And also he got an Young Scientist Poster Award in NIMS conference, Tsukuba, June in 2012, and he has got Best Presentation Award in 12th Conventional Electrochemist CRI Karaikudi. So he is a faculty advisor and research scholar from July 2014 onwards, and in NIT Warangal, and he's holding so many other responsibilities also. So it is very nice to have sir with us. Now I would like to give this mic to sir. So now sir will be taking the session now. Sir, we welcome you, sir. Please continue.
Yeah. Thank you, Dr. Rao, for an introduction, nice introduction. So good morning to everyone. And before I begin my talk, may I request Dr. Rao to give an overview of audience, means what's their background. So,
sir, audience are they are mostly faculty members, sir, and
okay.
faculty members and research scholars, and some students are also there. Some BTech students are also there. They
So mostly from mechanical engineering department, right?
Yes, sir. Mostly from mechanical engineering department.
Fine. Thank you, Dr. Rao. So now let me share my screen. So are you able to
Yes, sir. Yes, sir. It is coming.
view the presentation?
Yes, sir. We are able to see the presentation.
Fine.
Here we.
Yeah. Thank you. So then, shall I begin?
Yes, sir. Yes, sir.
Yes.
Please continue.
Yeah. So first of all, I would like to thank Department of Mechanical Engineering, Christian College of Engineering and Technology, Bilai Chhattisgarh, for providing me an opportunity to talk on this topic, that is friction stir processing, a tool for developing functional materials. So this is my topic. And outline of my talk is going to be as follows. So first let me differentiate what structural material from functional materials, and composites versus surface composites, and what are the methods available to prepare surface composites, and then how friction stir processing can effectively be used to prepare surface composites, and then what are the efforts underwent so far to produce surface composites through friction stir processing, and then is there any effort to produce functional materials through FSP, and finally, we have made some attempts to prepare functional materials through friction stir processing. So I will give you an overview of our own efforts, and then finally I will summarize. So let me start with this slide. Let me differentiate structural material from functional material. So structural materials, that the materials that are used primarily for their mechanical properties or load bearing applications. So they are expected to endure a certain amount of load during their operation. So even the building materials, bridge materials, these are all comes under structural materials. So the typical examples are steels, aluminum, magnesium. These materials are more like structural materials. And functional materials. So these materials are preferred for their specific properties. Apart from enduring load, they also exhibit some kind of special electronic properties, magnetic properties, optical or chemical properties. So for example, nickel titanium alloy. So apart from bearing load, so it also exhibits a unique property called shape memory, through which it is able to recover certain amount of deformation by simple heating or unloading. And there are some materials which I have shown in my slide on the right hand side. I have shown. So here the windows. So the windows are made up of some like a functional material, like applying a charge. So they orient the molecules in certain directions so that it will permit the light. So if I apply a different charge, so then these molecules align such that they don't allow any light. So then so it is, so apart from these materials are used to protect your cabin, okay, protect your cabin from outside atmosphere. So in that way it is acting as a structural material, and at the same time it is also exhibiting a special kind of optical property through which I am able to achieve certain function, that is whether I can allow light or prevent light entering into the cabin. So in this way, so the functional materials, in addition to enduring the load, so they also exhibit certain kind of functional property. And composites, I think being a mechanical engineers, you might have heard a lot about composite materials. So the development of composite materials start with the development of structures for aerospace applications, where aerospace structures require low density, strong, stiff, impact, abrasion and corrosion resistant materials. So it means we want, best in same material, but actually in nature, so we don't see all the best properties. We don't see all the best properties in a single material. So in that way, what we do, like we combine more than 2 or 3 materials in order to take their, individual components advantage. So that's where composites comes into picture. So generally, composites are multi-phase materials, because when you want the system has to exhibit several kinds of properties, then it is necessary to mix. So naturally, so they are functional multi-phase materials, and they are chemically, different. They are chemically different. So they may have, so for example, metal and ceramic, or polymer and ceramic, like that. So they have like their properties are determined by constituent materials. See, if you mix metal and polymer, so the composite will exhibit the property of metal as well as polymer. So in general, the microstructure of composite consists of 2 phases. So one is matrix phase, which is continuous. The other one is dispersed phase. So like uh, I'm showing a cake on the right hand side of my slide. So where this wheat batter act as a matrix, whereas this kind of almond particles or choco particles are dispersed in this cake. So a cake is a simple example for composite. So what's the difference between composite and surface composite? So here, so this one is you can say this is a monolithic material of a single phase. So when I mix something else, like which I am showing here, it is some yellow color particles are mixed in a blue color metal. So then it forms a composite. So like it's a mixture of 2 phases. So like the continuous one is called matrix, and the dispersed one is dispersite. So in case of surface composite, we don't turn the whole material into a composite as in the first case. We turn only the surface into composite. That's why we call it a surface composite, because why surface composites are more preferred by, or there are a lot of efforts to produce surface composites. Most of the time, you want some specific properties has to be exhibited only at the surface. For example, corrosion begins at the surface. So it is for me, the whole material doesn't need to exhibit high corrosion resistance. If the surface exhibits very high corrosion resistance, then I can prevent corrosion I can stop the corrosion at the surface itself. So the substrate material is completely preserved by the surface. So in that case, let me take another example, like wear resistance. So generally the surface is being, it's in contact with the other part. So in that way, like only it is necessary to improve the wear resistance of the surface rather than improving the wear resistance of the bulk material. So like this, most of the desired properties can be enhanced only at the surface. So we don't need to spend much money on converting the whole material into that composite. So it is enough to change the surface properties. So coming to your question, that is, what are all different methods available to prepare surface composite? So hot facing. So either by arc welding or gas welding or powder spraying or laser hard facing. Using these techniques, either you can modify the microstructure at the surface, or you can coat something special on the surface. So similarly, like in case of surface coating also, so there are several methods are being used: thermal spraying, chemical vapor deposition, physical vapor deposition. These are the methods used to change the surface microstructure or deposit something new on the surface in order to enhance the desired properties of the surface. Let it be a corrosion resistant, means let it be if I want that the interested properties may be improving the corrosion resistance, improving the wear resistance. So, or to achieve some kind of functional properties, a different kind of for example, like how the surface has to scatter the light. So like that, so the functional property may differ, depends on the requirement. So in this category, so the recent technique is friction stir processing. So in fact, friction stir processing is a modification of a process called friction stir welding. I think being a mechanical engineer, most of you might have heard this technique. So using this technique, it is possible to join the plate even in the solid state. Otherwise, in the conventional welding, we generally melt the parent material, and we take it, and then at the liquid state, both the metal mixes together, and then by solidifying them, so the joint is established. So but in this case, what we are trying to do, we are with a kind of by using a metallic tool, we are trying to stir, as I have shown in my right hand side slide. So what we are trying to do, we are just mechanically stirring the surface so that so there is a mixture of material, and thereby the joint is established. So um, so this is completely in solid state. So that means like when the metal melts and then solidifies, so there may be a shrinkage, and then because of this process, liquid to solid, because of the solidification process, so it may induce some kind of defects, and that I can avoid. And then it involves very high temperature. Naturally, there will be an oxidation or any kind of chemical reaction. So it will it enables diffusion of elements. So thereby there will be a compositional changes. So all these things can, to an extent, can be prevented by employing this friction stir processing. But at present, this technique is reliable only to establish joints, like for soft materials or non-ferrous materials. So like let it be a aluminum alloy, magnesium alloy, and to an extent titanium alloy. So in order to process steels, so very expensive tools are required. For example, single crystal or polycrystalline boron nitride tools are required to friction stir process steel materials. So um, so in case of before getting into how this friction stir processing is effective to produce surface composites, so uh, let me go through this topic. That is, uh, as an engineer, like what I look for in single phase microstructure. So if you take a simple pure aluminum or pure copper, that is a single phase material. So what do I look? So there I will just simply look for the grain size. So by changing the grain size, so you will be able to determine the mechanical property. So like finer the grain, better the strength at low temperature, means close to room temperature. Coarser the grain, better the mechanical properties at elevated temperatures. So like this, so only the only choice you have in single phase material is just to play with the grain size in order to get some desired mechanical properties. When it comes to composites, there are several, like you get more choices. In case of single phase material, only you can change the grain size in order to vary the properties. Whereas when it comes to metal matrix composites, for example, or let it be a ceramic matrix composite. So as I told you earlier, a composite has two kinds of structure, at least two features in their microstructure. One is matrix, the other one is dispersoid. So here the matrix can be like a single phase or multi-phase once again. So it can be it is made up of single phase material or multi-phase material. And then grain size, like by playing with the grain size, you will be able to modify the property. When it comes to reinforcement, their shape, their size, and then interparticle distance between these two, between the particles, and then how these particles are distributed. And what about the contiguity? Contiguity in the sense, sometimes if you put more amount of particles into the matrix, what happens? So these particles will touch each other. Okay, so your mechanical engineers, you might have heard about this ceramics, ceramic matrix composites. So in order to process high speed steel or very hard materials, we are using cermets. So cermet is nothing but ceramic matrix composite, ceramic metal composite. So where like in a cobalt metal, tungsten, very hard tungsten carbide particles are embedded. But if you see the fraction of these particles, so it used to be around 90%. So when you put 90% particles, there is a good chance that there is a one tungsten carbide particle touches the other tungsten carbide particles. So the fraction of this shared interface. Okay, so that's called is contiguity, and this also determines the mechanical property of the composite. So you need to, if to get a better property, we need to avoid this hard particles interface. So, and then nature of interface, whether it is coherent with the matrix or incoherent with the matrix. Generally, we prefer coherent matrix. So coherent interface for better mechanical properties. So and then what kind of, whether any reaction products have been formed at the interface. For example, in aluminum silicon carbide composite, so if the processing temperature is very high, then at the surface aluminum interacts with carbon and then aluminum carbide forms, so which is deleterious for mechanical property. So when it comes to metal matrix composite, so you have lot of factors or lot of choices with you to, in order to play with the mechanical property. So one, if somebody is trying to prepare composite using friction stir processing, then one should understand how all these factors are being influenced by friction stir processing. So let me take, so now what I do, so what I have listed in this slide, so I have listed what are all the features one will see at metal matrix composite. This is nothing but what you have seen in my earlier slide, and whatever I have written on the red color, so how friction stir processing influencing these features. Okay, so when it comes to matrix, of course matrix may have a definite grain size. So after FSP, the grain size reduces. And then when it comes to reinforcement, so you may have a very coarse precipitate or coarse reinforcement before FSP, but these precipitates are refined or break down by FSP. And interparticle distance, so the interparticle distance is altered after FSP. So, and then how it distributed, so previously it may be inhomogeneously distributed, but after doing FSP, so you may get a very uniform distribution or vice versa. So coming to contiguity and nature of interface, and then reaction products, so all these features will can be altered after after FSP. So all these things will definitely influence the properties, so that we have to keep it in mind. So here what I did, like in my earlier slide, I have just given like in terms of words, but here I am showing you in terms of microstructures. So what FSP does, so before so what I'm showing here is, so EBSD maps of pure aluminum before and after FSP. Before FSP, so you hardly see maybe 3 to 4 grains. Okay, but after FSP, you are seeing several grains. So in this case, like the grain size is reduced after doing FSP. And by means of FSP, you will be able to incorporate some particles. That means you will be able to produce composite. So we have taken pure copper, and then we have distributed tungsten particles into pure copper. So that way we have produced a copper tungsten composite. And here, so we have we have refined the microstructure, so of zinc magnesium alloy. So what you are seeing at here on the right hand side top microstructure is a zinc magnesium alloy. It's a two-phase alloy. So it is a zinc plus zinc manganese intermetallic. It's a mixture of these two phases. So, but after doing FSP, you just see you are unable to distinguish these phases. Here, I am clearly seeing the presence of two phases. One is dark color and then other one is brighter. But here, it is completely mixed. So, like this, you will be able to drastically alter the microstructure, and thus in turn will have a significant influence on mechanical properties. Dr. Rao, so is it going well? So
Yes, sir. Yes, sir. It is fine, sir.
uh, and like how this microstructure evolves during FSP. So like what I'm showing at the top is like a pure material, pure aluminium, and then after being FSP, after conducting FSP, how its microstructure alters. So you will see some U-shape, U-shape in this like plate, this aluminium plate. So what is this? So this is like this zone is the microstructure is completely altered after FSP. So before FSP, like grains are very larger, you are able to clearly see this. But after doing FSP, it is at this magnification, we are unable to distinguish the grains. And then like with any other welding technique, like we have parent metal and weld zone, and then in between we will be having this heat affected zone. So that is a typical microstructure of any welded component. So here also we are having thermomechanically affected zone, and then in some cases we are having heat affected zone. So we have four kind of zone. So parent material, and then heat affected zone, thermomechanically affected zone, and stiff zone. So like we have some four kinds of microstructure after FSP. So what causes this microstructure what causes this microstructural evolution in FSP? So as you might have seen in my earlier slide, so what we are trying to do, we are trying to stir the material with a hard tool rotating at certain speed, and also it travels on a line, so on a straight path. So because of this stirring, so we are imparting a certain amount of strain into the material. Then that strain results in formation of some kind of dislocation. At the same time, so the rubbing of tool against this your workpiece generates heat. So simultaneously, you are deforming the material. At the same time, there is a generation of heat. So in fact, this generation of heat assists the plastic flow. So plastic flow. So when you have when you impart certain strain, and otherwise like when you have a lot of dislocations into the material, and then when there is enough heat is available, then it is it will evolve as a new grain. So that's why the microstructure is refining after FSP. So generally, like the recrystallization temperature used to be 0.4 to 0.6 times of melting point of the material. But here, the recrystallization temperature, maybe even it can happen to 0.2, 0.3 times of melting point of the material, because so there is a lot of plastic deformation. So this strain imparted into the material together with the heat is good enough for the material to recrystallize its microstructure. So this is what we call a dynamic recrystallization. So during this, if the heat is good enough, then what happens? So there could be if your material has some kind of precipitate in the before FSP, it may dissolve if the heat is good enough. Or sometime what happens, like the new precipitate may form. So it all depends on how much heat is produced during FSP. So this is how the microstructure evolves during FSP. And when it comes to, so when I say heat, so what what are the parameters controls this? So there are three kinds of process parameter: machine variables, tool design variables, and material properties. So when they say machine variables, so the tool at what speed the tool rotates, at what speed the tool travels along on the material, and then tool tilt angle, and then tool plunge depth. So these are some typical machine variables. Among these, if you conduct a literature survey, so many literatures are suggesting that tool rotational speed and tool travel speed are two major parameters which are being used to control the microstructure. When it comes to tool design variable, tool shoulder diameter and tool prop diameter. So it is simply a typical, like what you are showing, what I am showing on the other side is there are different kind. Either you can use a simple cylindrical tool. It's a kind of pen kind of tool. So you can use, or you can use some threaded joint or stepped spiral pin. So you like tool profile. You can use a different tool profile, and then like you can use a different diameter cylindrical pins, and then the same thing for the probe also. So it can have a different diameter, it can have a different profile, and then height. So it can have a different height, varying length. So, and then material properties, so mechanical and thermal properties. So let us keep these material properties aside. So if I like from this, so what I the key properties are the tool diameter, and then tool shoulder diameter, and then tool rotational speed, and then tool travel speed. And these are the some very key very key process parameters. So what happens, what I'm showing, so I'm showing some equations on the other side. So if I see, so what is the maximum temperature develops, okay, in a particular, when you do FSP, and then with respect to the melting point of that particular material. So that is proportional to the rate at which the tool rotates, that is omega, and then the tool travel speed. So that means if I increase the tool rotational speed, then the heat input into the material increases. If I increase the a tool travel speed, then the heat input into the to the material, it decreases. So tool rotational speed and then tool travel speed, these two are very important to decide how much heat is being transferred during this process. That's very, because this heat only will play a major role in microstructural alteration, as I described in my earlier slide. So selection of these process parameters are essential in order to get a very healthy processed region. So for any material processing technique, here also choosing proper process parameters in order to evolve a very good microstructure, means a very good in the sense defect-free microstructure. So here in this slide, improper choosing of certain parameters, how it will how it will lead to producing some kind of defects, and that what I have shown here. So if you keep on increasing the tool travel speed, then what happens, that there is a generation of wormhole. So this is nothing but a wormhole. So that means throughout the section of the processed region, there will be a hole inside. So why it is so? So because when you travel at very high speed, so the heat may not be enough to completely plasticize the sucked volume. So in that case, what happens? So a hole develops throughout the path of that tool. So that's called wormhole. So similarly, like there are several kinds of defects, and then it is being caused by certain kind of process parameters. So the key point here is one has to optimize the key process parameters like travel speed and rotational speed in order to produce very healthy billets, healthy process zone. So the next topic is how to prepare surface composites via FSP. So excuse please. So thank you. So how to prepare surface composites through FSP. So first we take a simple plate, and then over the plate we are machining a rectangular slot, and then we are filling the rectangular slot with the reinforcement, and then we are doing FSP. So then this zone is nothing but a composite. So if you if you run some 2 or 3 subsequent passes, so then what you will get the whole surface turned into composite. So yeah, this is what that I have just magnified this portion.
Okay.
Hello.
Yeah, it's fine, sir.
Hello, sir, Dr. Rao, shall I continue?
Yeah, sir. You can continue.
Yeah, fine.
Hello.
So the second method is what we can do. We can drill holes of different depth. So
Please continue, sir. Please.
yeah. So then these holes are filled with different kinds of these holes are filled with the required reinforcement, and then you can do this FSP. So by this you will be able to vary the reinforcement content from one end to another end. Thereby you are not only producing composite, you are also producing functionally gradient composite. That means in one end you will have very high amount of reinforcement, and the other end you will have very low amount of reinforcement. Thereby you will be able to produce a surface composite, also some variation in the properties. So the other thing also, this is also in the same way, that is like you can drill the same depth but a different diameter, and thereby you will be able to incorporate different amounts of reinforcement from one end to the other end. So you will be able to generate surface composite at the same time you will be able to generate a functionally gradient microstructure. So like this. So of course there are, if you go through the literatures, you will find some more methods of developing surface composites through friction stir processing. So what I'm showing here is what different what are all the surface composites developed through FSP. So if you go through this slide very carefully, so you will understand that most of the time, most of the people have chosen aluminium as a matrix. So it can be a pure aluminium like 1100, or it can be a aluminium based alloy. So like for example 2024 or 5083 or 7050. So people have chosen. So here I have limited to only certain alloys, but otherwise if you go through the literature, you will find all kinds of aluminium alloys, right from 1 series to 8 series have been chosen as a matrix material. Then when it comes to reinforcement, silicon carbide, tungsten carbide, boron nitride, boron carbide. So there are people have used several kinds of reinforcement particles to reinforce aluminium matrices. And if you see, once they construct a composite using this technique, what kind of properties they have studied? Mostly they have characterized their mechanical property, that is tensile strength, hardness, and wear resistance. So very few people have developed developed functional materials through FSP. Functional materials through FSP, that is by incorporating a reinforcement with a specific set of magnetic property or electrical conductivity or thermal conductivity. You will be, in addition to changing the mechanical property, you are also able to change some kind of functional property, and that functional property can be anything: magnetic, electrical, thermal, or damping, everything. So let me give you some example. Like some people have some researchers, what they did, they have taken aluminium alloy, for example 2024 or 2014 aluminium alloy, and then in that they have mixed nickel titanium particles. So this nickel titanium is a very popular shape memory alloy. So what they tried by adding these things, so nickel titanium shape memory alloy has a very good damping property because of its phase transformation behavior. So thereby, like, you can improve the damping property of aluminium by incorporating nickel titanium. So what you are trying to do, so by incorporating this nickel titanium into aluminum, you are changing the mechanical property, because nickel titanium is mechanical properties are better than aluminum. At the same time, nickel titanium enhances the damping property of aluminum or aluminum alloy. So thereby both the properties are changed. So if some research scholars are attending this talk, so if your work area is friction stir processing, don't stop your research with investigating mechanical property. That is, you may be taking some kind of base material, and then you may be reinforcing some kind of particle, and then you may be investigating only mechanical property, and mechanical property in the sense hardness, tensile strength, and wear resistance. So maybe corrosion resistance. So don't stop your research up to that point. So do characterize those material for electrical conductivity or thermal conductivity or some kind of magnetic property or damping property. Thereby you can bring some kind of uniqueness to your research work. So what I'm going to, so far what I was trying to say, that how FSP can be used to prepare surface composites, and then how this technique can be exploited to produce functional materials. So if you go through the literature, so you have some reasonable amount of literature, literature available to effectively use this FSP for functional material development. And what I'm going to share hereafter. So we have also, in our laboratory, we have also tried to develop the functional properties of some materials, and then I am going to share two such examples hereafter. So so first, actually, development of high strength, high conductivity. That's what this HSHC stands for. High strength, high conductivity copper alloys. So if you take pure copper, it has 100% IACS. That means we assume the pure coppers, annealed coppers electrical conductivity is 100%. So that's what 100% IACS, International Annealed Copper Standard. So 100% IACS. The pure copper has only 40 HRB hardness, and then tensile strength is only around 210 megapascal. But in order to use pure copper in the application, which I have shown in the bottom of the slide, like electrodes or switches, so use of pure copper is not recommended because of its very poor mechanical property. So in such case, I need to improve the strength as well as conductivity. So what is the remedy now? I need to improve the strength of copper. So the first method is you alloy copper. So alloy with chromium, or alloy with zirconium, or copper chromium, or tin, or manganese, or magnesium, or tungsten. So you can do, you can produce alloys of copper, but the problem is, once chromium into chromium or zirconium or any other element into copper, so they try to scatter the electron movement. Okay, they try to scatter the electron movement, thereby they reduce the electrical conductivity, which I don't want to have. So that will reduce the electrical conductivity even down to 40% ISCS. But so what is the remedy now? So is it possible to develop a high strength, high conductivity material through FSP? So that's what we have explored in our work. So what we did, we have chosen pure copper, and then we have applied FSP, we have processed through FSP. We studied its mechanical property and electrical conductivity. And we have chosen some commercially available copper alloys. So which I have listed here: copper chromium, copper zirconium, copper chromium zirconium. All these alloy exhibit 70 to 80% of 80% ISCS conductivity. So so is it possible to improve the strength of these alloys without deteriorating its electrical conductivity? That is the objective. And then what we thought of preparing some composites using FSP. So copper tungsten, copper graphene composite. So we are thought of developing this kind of composites for through FSP, so that whether I am able to improve the strength at the same time without deteriorating the electrical conductivity. And that is the ultimate aim of the work. So So this is one good result. What we have got is copper graphene composite. So in this case, like after doing FSP, so what you are seeing here, like you are seeing a very coarse microstructure. So around 40 micron grain size before FSP. But after doing FSP, like the grain size is reduced to somewhere 1.5 to 2 microns, and it depends on the travel speed. So we have what we did, we varied the travel speed, we fixed the rotational speed, and thereby we studied how the FSP affects the grain size. At the same time, how effective it is distributing graphene. So in all these processes, through Raman spectroscopy, we confirmed that graphene is uniformly distributed in the stir zone, and the grain size reduced from like 40 micron to minimum of 1.5 micron. And the good thing what we have got through this research is like the decrease in electrical conductivity. So I am sorry for poor graph here. So like the electrical conductivity without, like in as received state, it is very close to 99% ISCS. After incorporating graphene and refining the grain, the electrical conductivity is around 97.5. So that is around 1.3 to 1.5 ISCS decreased. That is, decrease in electrical conductivity is very less. But if you see the wear rate, it is drastically reduced after FSP. So hardness also increased. So the point is, we are by through FSP, like we improved the strength significantly. At the same time, so there is an insignificant change in electrical conductivity. So that objective, to an extent, this objective, our objective is achieved through by employing FSP technique. So, and what we did, copper tungsten composite is one of the successful copper composite available in the market. So the problem with available composite in market is, so they have very poor electrical conductivity, because tungsten has very low electrical conductivity. So when you add tungsten into copper, then copper's conductivity also decreases. So what we were trying to do is, instead of putting more amount of tungsten, we put less amount of tungsten and then improve the strength by FSP. So is it possible? So once again, so the wear rate is significantly reduced, and at the same time, so if you see the conductivity is not decreased that extent. The conductivity is decreased only around 1 to 1.5%. That's it. So this is possible because, like by FSP, we are introducing new surfaces. Nothing but we are refining the grain size, and thereby we are introducing lot of surfaces, and that really helps to improve the strength. So you might have also heard about Hall pitch strengthening. So when you decrease the grain size, so the strength of the material at room temperature improves a lot. This is because grain boundaries are effective in preventing the motion of dislocation. Thereby we are improving the strength. So, and our next effort is, so is it possible? So in the earlier one, so in addition to improving the structural property, there is nothing but mechanical property, we have improved the electrical conductivity. Not improved the electrical conductivity, we have not deteriorated the electrical conductivity. So we were able to achieve certain functional property there. So in the second effort, so we try to produce some high damping layers. So in general, metals are poor dampers. So whenever you want more damping, people always prefer polymers. They absorb more vibration. Whereas in case of metals, it is very less. Among the metals, magnesium is a kind of, magnesium having very high damping. Okay, tan delta is around 80. So it is having very high damping, and and so far we are using FSP or FSW just to make joints or alter the microstructure and then alter the mechanical property. So what we have investigated here is it possible to change the damping through FSP? So damping is one kind of functional property. So damping is influenced by that inherent damping, means every material has its own damping, and then that microstructure. So by altering the microstructure, also you will be able to change the damping. So this microstructure can be engineered by FSP, and that's our aim of our means that's the motto of our research work. So through FSP, is it possible to alter the microstructure, thereby damping property? So what we have done, like we have processed some aluminum, like aluminum, copper, magnesium, metal, or we have chosen some aluminum alloy, 606 and aluminum alloy, and we also prepared some surface composite. And then we have characterized this damping property using dynamic mechanical analyzer, and there is a technique called impulse excitation technique or resonant frequency damping analyzer. Using these two techniques, we have analyzed the damping property of our FSP materials. So what I'm showing here is, so like in case of pure aluminium, we were able to decrease the grain size from 44 to 10 micron after FSP. In case of copper, 20 to 4 micron. In case of magnesium, it is 780 to 25.6 micron. So the grain size was very coarse in the acid-received material, but it is greatly refined after FSP. And then how this influences the damping property of the material. So what I'm showing here is, so all these graphs are nothing but amplitude, means amplitude of vibration with respect to time. So how effective the material damps the vibration. So if you see here pure aluminium in this graph, so it takes very long time for the vibration to die. But whereas here, like after FSP, it is somewhat significantly reduced, but it is not that evident. But if you see copper, so it is clearly evident before FSP, like it takes, the pure copper takes very long time to damp the vibration. But after FSP, so you see that that vibration dies very quickly. So that means the damping property of pure copper is significantly enhanced just by doing one pass of FSP. So the same thing I have shown here. So pure aluminium damping property is increased 1.5 times, whereas damping property of copper is doubled, whereas damping property of magnesium after FSP decreased. So greatly decreased, in fact, if you see. So this is because how this magnesium damps the vibration. So in fact, so the movement of dislocation has to be allowed in order for effective damping. But what happens in magnesium after FSP, it FSP produces a lot of dislocation tangles, and these tangles are not allowing dislocation movement during vibration, any external vibration, and thereby it reduces the damping property. Whereas in the other materials, it increases. So that is, so whatever I have shown here, it is at room temperature, but the same thing is shown at high temperature also. So that is the properties of pure copper and pure aluminium greatly enhance. Whatever you are seeing in red color in this plot is nothing but damping property as a function of temperature, how damping changes with respect to temperature. So the red color one is for the FSP one. The black color one, black color curve is for the acid-received material. So in all these cases, you will immediately you can come to a conclusion that at high temperature, FSP materials are good in damping the vibration. And this is because of large fraction of grain boundaries. Generally, grain boundaries are amorphous in nature. So under external loading conditions, these boundaries will move and then thereby it absorbs the external vibration. Yeah. So we have also produced 6061 graphite composite. And then here, what I'm showing here is like how the damping property increases after doing FSP with respect to frequency. Y-axis in both the plots are damping. In the first plot, the x-axis is frequency. That is, when I change the loading frequency, what happens to damping of the material before and after FSP. So when I change the temperature, what happens to the damping before and after FSP. So here immediately after FSP, there is a significant increase in damping. Not only by FSP, by addition of graphite also, the damping improved a lot. And that's what we have shown here. And in fact, in all these cases, after by incorporating the graphite as well as FSP, we were able to increase, means we were able to increase the damping double or triple. So that's the point I would like to convey. So similarly, like we have incorporated like silicon carbide particles. So and then this silicon carbide. So what we are seeing here is, so we have incorporated 3 different sizes of silicon carbide particle, and then we have studied what is the influence of particle size on determining the damping. So we found that by incorporating very large size particles, that's what you are seeing in this blue color. So by incorporating very large grain size, large particles, we are able to increase the damping more effectively. So if you see, the as-received alloy is only around 0.01 and then less than 0.02. But if you see here, so at the same temperature, aluminum silicon carbide composite, the damping used to be around close to 0.06. So that means it is increased to 3 to 4 times. And when it comes to like not only ceramic particles, if you incorporate iron or nickel into 6061 composite, 6061 alloy, that also increases the damping, and that's what we are like I'm showing here. So in all these cases, so by incorporating nickel or iron, so we were able to improve the damping. So in this plot also, like if you see here, so after incorporating particularly this is for as-received material, and then this one is for FSP. But if you see the bottom 2 plots, when you incorporate iron or nickel, the damping is greatly improved, and that's what we are seeing here through these plots. So the summary is, I don't want to go by step. So thing is, like the damping property greatly enhanced after FSP, and also by incorporating silicon carbide particle or iron or boron nitride or nickel. So we have effectively used the FSP to alter the damping properties of the material, in addition to improving the mechanical property, and that's the key message here. So there are several efforts have focused on enhancing the strength, hardness, and wear resistance of aluminum alloys or magnesium alloys by FSP. But what in my talk, what I have shown now is FSP can be effectively used to develop functional properties. Okay, and also I have shared our own experience in improving the functional property, that is like preserving the electrical conductivity or enhancing the damping behavior of aluminum or copper alloys. So I would like to acknowledge Dr. Madhusudan Reddy. So in his laboratory only we have conducted this FSP. So and then Sri Rama Rao, DRDL, and then for helping us in conducting some damping studies, and then my first PhD scholar B.K. Nayak, and then other PhD scholars Venkat and Vidish Nayak for their help in doing the experiments. So thank you all for listening. I know it's very tough to listen to online talk, and I would like to thank the organizers for this great opportunity. And yeah, so stay home, stay safe. So thank you. So now you would like
Thank you, sir. Thank you very much. Please.
Yeah, thank you, and then I welcome like if any questions I would like to answer.
Sir, good morning.
Good morning, sir.
हाँ, my question is that sir, ये जो अपना जो अपन FSW जो प्रोसेस अपने किया वेल्डिंग के थ्रू, तो
sir, I'm sorry, sir. Actually, I don't understand Hindi. So, sir, please be.
Okay. After FSW welding process, there is a need to any heat treatment process.
Any
heat treatment
sir? No, sir. We have not performed any heat treatment after FSP. All this, like whatever I have shown here, is just after FSP we have characterized this mechanical as well as electrical conductivity or damping. But if you want to apply some heat treatment procedure, yes, you can do that.
Oh, okay. There is any problem of the distortion after the FSP?
No, sir. Like
There is any chances of distortion after FSW process?
immediately after FSP, in fact, whatever the process parameters which I have shown, that is use of 600 RPM or 900 RPM, and varying the travel speed from 50 millimeter per minute to 200 millimeter per minute. So we didn't observe any distortion into the sample. But when we use very high rotational speed, tool rotational speed, so we found, bending of plates, some kind of bending of plates that we have observed, but we have not chosen those parameters because as our intention is something different. So we have not chosen very high rotational speed or very high tool travel speed, which resulted in some distortion. Yes. So yes. So
Will you give your PPT, sir? Because we also need a more study for that.
yes, sir. So yeah, I will share with Dr. Rao. So
Okay, sir. Okay, sir. Thank you.
so
Hello. Hello.
Any other questions from participants?
Hello.
So feel free, and then so that I also learn from you. So
Sir, FSP can be used for only flat surface, or it can be used for any shape?
is it for?
Any shape, or it will require only flat surface for FSP?
No, sir. It's a flat surface.
Only flat surface.
So far, I have not come across, so far I have not come across any method to process these wavy surfaces. But yeah, so far only the flat surfaces.
Yeah. Thank you, sir.
Any other question from participants? Please, you can post it in the chat box or you can ask directly. Okay, I hope Sara has answered all your questions. So once again, I would like to thank Dr. Arokya sir when we asked sir to take a session in our college through this webinar online meeting. He has accepted our invitation, and in spite of his busy schedule, he has given us the time to share his knowledge with us, especially on friction stir processing. It is one of the active research field nowadays. I visited NIT Warangal 2-3 years back. That time there were so many people, research scholars were there who were doing this in friction stir processing. So I greatly acknowledge Sir also. Was really helpful to us, especially in sharing his knowledge. And I thank you all the participants for participating from 18th July to till 23rd July. So in this e-faculty development program organized by Mechanical Engineering Department, CCET, Christian College of Engineering and Technology, Bhilai, Chhattisgarh. So I hope that you have equipped with the knowledge that has been shared from 18th July. Dr. Rahul S. Malik is from IIT Roorkee. He was taking the lecture yesterday on manufacturing process, and today also Sara is taking friction stir manufacturing process. So yeah, Dr. Dharmendra Shukla from NIT Allahabad, NIT Allahabad, he has shared, and Dr. Anil Kumar Viru from NIT Manipur, he has shared on the dental crowns manufacturing. So like that, we all have listened many things. So I will be sharing. We organizers will be sharing within one day, maybe by tomorrow night. By tomorrow night, you'll be getting the feedback link. you please fill the feedback link, and as soon as you fill the feedback link, you will get automatic certificate also. So yeah, so and once again I thank all participants, and especially I thank our college also for helping us and motivating us to organize this faculty development program. College management, principal madam, and all everyone. I will would like to thank each and everyone. Especially I would like to thank our organizing team also, Dr. Radhesham Kachkar sir, and Dr. Roshita David, and all our mechanical department faculty members who are there, backbone of this program. Thank you all once again, and I thank Arokya sir also once again for giving his excellent presentation on textile business. Thank you all. Thank you once.
Thank you,
Once
sir.
again.
Thank you, Dr. Rao.
Okay, thank you, sir.